Hello, everyone. Today, my topic is how to do multi-host inference for LLM, large language model, on Kubernetes. This is the maintainer track of the LWS. I am K, and Yin has also, we are LWS maintainer, but Yin cannot hear because of the visa reason. So only I can present to you. I want to share most valuable thing to you. This is the agenda. Firstly, I will talk about the challenge of multi-host inference. Then I will introduce the LWS project. Next, I will talk about the in practice, how to use the LWS. Finally, the LWS ecosystem and the roadmap. So let's go to the first part, the scalability challenge of the LLM. Before we talk about how to influence in multi-host, let's go to the hello world in single node. It's very simple and easy. If we want to run it, we can only just buy a Docker run with GPU and using the SGLang or vLLM influence engine. Then so launch a container with the model path such as Llama or DeepSeek or anything, so that we can get a port using HTTP. Any LLM client can use it to inference, get the result. That's very simple and very easy. But the LLM size is growing. Recently, the partner size is very big. For DeepSeek is 600 parameters, and the Llama is very big too. So one machine cannot host the one model. For example, this is the DeepSeek R1's hardware requirement. If we want to inference that we maybe need 2 machines or 4 machines. If we are one machine very big GPU memories, that can do it. So because the mode is way bigger and bigger, we need more machines to serve one mode. Another important reason is that if we use multi-machine, the throughput can be improved. It not only improves the total, the throughput per GPU, not total, can also improve about 10%. So this is the data from the NVIDIA's benchmark. We can see if it's about 10%, 10 times to improved. So that's very useful. That's the 2 main reasons why we distributed inference. And another reason is autoscaling. If we use multi-machines, when the workload is heavy, the nodes can be autoscaling. And another reason is the GPU is always often failure. So it's important to do some failure things that to increase our scalability. So let's introduce the LWS set to do this. This is a picture of the technology about Kubernetes to serving for the GenAI. For GenAI, there are 2 main workloads. One is serving, one is training. So the Kubernetes built the 2 technologies for it. For inference, we use the LeaderWorkerSet. And for the training, we need JobSet. That is new things. And it can also be using traffic management to serving by the users. And we also have the DRA and the queue to management the GPU and the network resource. These are this project, the LLM aware routing gateway API. The JobSet is a native API for distributed machine learning training, and the LWS LeaderWorkerSet to enable multi-host inference. And the queue is a Kubernetes native queue. And the DRA is the next GPU operator for Kubernetes. So what is the LeaderWorkerSet? It can easily to understand. There are many workload architecture is a leader and many workers. It's like a super pod. One pod is a worker have many pods. So it's a super pod, can work together. So it's named LeaderWorkerSet. This is a simple YAML for it. A LeaderWorkerSet is a CR in Kubernetes. And it can create a stateful set for leader and a multi-stateful set for worker. And the replica, there's 3 replicas for them. Each replica called a group. It's a HPA unit and a fault domain. And by the way, it needs a new Kubernetes versions to do it. So let's do some one-on-one. We can think a group is like a boat. This man is a leader. He wants the boat to move, so there need a worker. Well, we need more worker, so the worker size is 2. We need more worker, the worker size is 3. When we need more boot, so there are 2 boot. So replica is 2. There are 8 pod for it, 2 leaders and 6 workers. So this is LeaderWorkerSet. This is the features of LeaderWorkerSet. It can group the pod as a unit. These features we'll talk next slides. So I can introduce it simply. It has 2 templates, a leader, a worker. It can do the firing handling. It can rolling out. And it also can do auto-scale, topology-aware replacement, and subgroup. So firstly, this identity. That's very important. For example, they also have a number. The 0, 1, 2, 3, 0, 1, 2, 3, they are numbers. The numbers can be injected with environment variable to the pod. So each pod know what's the number of itself. Another thing is all or nothing restart. We know the pod in LeaderWorkerSet, they are tidy. They work very tidy. Any one of them is fail, the whole replica should be fail and restart. So this is the feature for it. And we also can configure it with the restart policy to know. So its behavior is like normal deployment or normal set. Another feature is rolling update. We can configure it. It's very similar with like deployment or set. We can say much unavailable is 2. So in any time, 2 replicas can work. It makes the inference 0 downtime. We can also using auto-scale with AWS. So the architecture is like that. We use Prometheus to pull metrics from the pod, and then use HPA adapter to get the metrics and decide when to auto-scale it. When we want to scale it, it can increase the replica. So this is the architecture. And an interesting topic is that which metric we should use for the auto-scale of AWS. Different from the deployment, we use the CPU or memory metrics. We often use the numbers of requests waiting in the vLLM queue to decide when to auto-scale the replica of the inference. That's a little different. So let me show some demo for you. We can decide, this is the HPS config. The scale target is the LeaderWorkerSet. Then this is the demo. Yes. We can get the metrics from the Prometheus. It's a request waiting in the queue. If many requests are pending to be inferenced, so the queue may be increased. And this is a service monitor to get the metrics. So we apply it. Okay, it has been applied. This is a benchmark tool. We can using it to benchmark the inference server. So the metrics were increasing. Now we can see it's 100. So the replica has been increased. The more pods will be created. Firstly, there are 2 pods. Now there are 6 pods. So this can be running. New pods is being created. Okay. Then the benchmark will be finished. The matrix is decreased. Then the replica will be slowed down. So it's scale in. So the replica is 3. It's shutting down, terminating. This is the matrix, increase and decrease. Okay, this is the demo. Then the next feature is the topology-aware replacement. Now the GPU cluster technology is changing every day. In old days, there are PC server with GPU, and now there are GPU with NVLink or SuperLink technology. That is, for example, the DeepSeek GPU cluster. The next, in the future, the supernode is more high performance. It can work like many GPUs can work together. So the network, the topology aware is more important because the network in the inner trunk, the network each GPU can connect together. There are many, they are high speed. And if we in the PC servers cluster, the topology aware is not very important. But in the supernode, it's very, very important. So that's why we need this feature. For example, when we want to deploy the distributed inference, we can place each group in different rank. So we can use the annotation with exclusive topology. We can use anti-affinity to make the leaders to deploy in different ranks. Then the workers can using the affinity to deploy them in the same rank. So the network between them can be very fast, so the performance is the best. The next thing is supergroup. If the workload is very complex, it needs supergroup. We can talk it later. So, and it's the LWS in practice, the next part. There are some use cases of the LWS. For example, the multi-node distributed LLM inference, such as vLLM, SG-LLM, and Llama CPP and others, Ray. And it's also useful for disaggregated serving. And the other 2 rows use case is acceptable. Firstly, how is the mode sharding in the inference engine? For example, DeepSeek is a huge model. How we can use multi-GPU to serve it. There are 4 technologies: tensor, pipeline, data, and expert paradise to sharding it. If the TP way, you need the high-speed network between GPUs, and the PP is better performance. And the PPA needs not needs as much as network of it. But it's slower. So the best practice is we can use we can set the GPU numbers of the node of the GP, and the PP is the number of nodes is the best practice. For example, if we want to run a multi-node vLLM serving, how we can run without Docker, without Kubernetes. In the first node, we can use array start, and its role is head. And in the next node, we can start another array as a worker and join it. Then we can run with the vLLM to serving at the first node, so we can get a vLLM cluster with the multi-serving. If we use the LWS, it can be the same way. LWS has two templates: one leader template, one worker template. So we can use the almost the same command in the leader template, and the array start in the worker template. The interesting thing is that we can declare the variable for it, not to write. We can use environment variable to auto-enjoin to it. Let's see some demo. This demo, we can serve the small model with TP is 2. So it's the YAML for it. We can create a LWS YAML. We can see we use the bash command to start as the leader template. There is a script for the start command line. We can see that the script is being merged to the vLLM GitHub repo. It can start as 2 roles, leader and worker. If it starts as a worker, it can join to the leader. And this is the worker template. So let's see the demo. We apply the YAML described before, so we can get 2 pods. And we can also get 2 services. One service is to the vLLM leader, and another is to the group. So it's starting. Let's see the logs. This is the leader's log. It's that array, and waiting the worker to join it. Let's see the logs of the worker. It also starts the array and join the leader. So it may take some time. Okay, the array cluster has been set up, complete setup. Then it will to start the vLLM inference ranging. It will download the mode and load the mode into the GPU memory. Okay, it has been started. It might take a little time. If the mode is very big, it needs to wait a long time. Then we can use the CURL to call the mode. We can see the log. It's OK. And all the metrics and other HTTP endpoint. OK, that's the demo. Another use case is disaggregated serving. It can improve the serving's performance. There are two phases of the serving. One is the prefill, and another is decode. For example, if we want ask the LLM, the input token is, do you like Tokyo? And the mode get inference engine get the information, and they think, and for a long time it will return maybe fast. It's nice and clean. So the two phases need to share the knowledge. The knowledge is called the KV cache. This is the process of disaggregated serving. Input to the prefill. It needs a lot of GPU time. And the context be saved to the KV cache. The KV cache may be stored in the GPU's memory or other technology. And then is the decode. The decode the goal is to max the transport. So it can get the other tokens. That is the process. To implement the disaggregated serving, there are two ways of LWS to do it. One is subgroup, and another is using multi-LWS. If we use the subgroup, we can declare different roles of the LWS worker. But they are in the same ray cluster. And with the multi-LWS, we can create two instances of LWS, one for prefill and another for decode, and use the deployment to create a proxy for them, and use another tokenology to create the KV cache store. There are more discussion in the GitHub. We are looking to build a new orchestration on top of LWS to do this. This is the subgroup way. We can use different roles to serving this. We can use a script to decide which work pod is for the prefill and which is for the decode. The multi-LWS is simpler. I think it's better for the disaggregated serving. Okay, the final part is the AWS ecosystem and the future. LWS is one of the most widely adopted practice. Both the many inference engine has think it's a good way to serving. For example, the vLLM, SIG-Apps, and NVIDIA Dynamo. And many cloud is also Google Cloud, AWS Analysis. And the hardware is also support. For example, the NVIDIA GPU and the Google TPU, and many integrations. And another practice is that the AWS can work very good with queue. Queue is the Kubernetes native queue. For example, we can declare this as labels in a queue so that we can co-locate training and inference workload in the same cluster. The inference workload is heavy at the day, but at night, not many users use inference. So we can use the same clusters for training. That improves many GPU utilizations for the cluster. It's very useful and can make our cluster more cheaper. And there are many AI inference stacks are created this year. For example, Dynamo. It's created by NVIDIA. And it can increase the throughput of the inference many times. We can see its architecture is very similar. It uses prefill workers, decode workers, and smart routers, and KV cache. It's the best practice. And it's also used the LWS. And there are many other technologies, such as vLLM protection stack, Ibex, and LMD are also best other solutions for inference stack. And they are also integration the LWS now. So if we want to build inference with GPU, there are good solutions. not only AWS. There are many ongoing functions. This is a roadmap for AWS, such as downscheduling with the Volcano community, and the resource climb template with the DRA and many others. For example, to make the worker set mutable and partition update support and rolling update and others. So most the KEP can be found in the repository. By the way, the AWS is a project of the Kubernetes. It's a sub-project of Kubernetes. So we can find it in the GitHub repo in Kubernetes 6. And we also have a website and a new logo. If you want to join us, we can contribute the code and join the Slack to work group serving. It's a sub-project of the work group serving. There are many other things, good things there. Thank you. It's the QA time. Okay. Okay.
Thank you so much for your presentation. That gave me the perfect overview of the LLM serving. And I have a question about the LLM serving in framework like vLLM and SG-Lang. You showed the in the autoscaling slide, you mentioned about the vLLM custom matrix. So,
yeah.
Would you prefer using vLLM? I wonder if the other framework provides a necessary custom matrix to support autoscaling.
Do you mean for SG, any other frameworks that have customized metrics? Yeah. I think that is interesting that the VM's metrics part is also contributed by the Kubernetes team. So if we are also very interested to contribute more metrics part to the SG or others. I think it's very useful. It's not only for the AWS, it's also very useful for the gateway API.
That's interesting. Thank you.
Okay, thank you. Thank you.